Good morning. My name is Rodrigo Obando. I'm with the TCF School of Computer Science at Columbus State University, and I'm going to be talking about the genetics of cellular automata. So let's get started here. I'll leave the abstract there for whoever wants to download the presentation. So I'm going to go ahead and start with the talk. So we have used cellular automata to explore many areas in science, and they normally serve as a simple model to start investigating. And many researchers will discover cellular automata rules that simulate or model particular behaviors, and they have proven to be very useful. Of course, through the years, you hear rules such as 110 or 30 in elementary cellular automata. The first one is classified as class 4. The second one is classified class 3. Class 4 is complex. Class 3 is random. We also have class 1 and class 2. These are Wolfram's classifications. And all this has been done for many years. If you actually go back, I think we are like 75 years since cellular automata were proposed by John von Neumann. We've done this, and there are many kind of interesting things that we do. There are, in one-dimensional cellular automata, which is in particular what I'm talking about today. The size, and all the other ones, of course, as well. But the size of the space, each one of the spaces depends on the number k of possible values on each one of the cells. And the number r, which is the number of neighboring cells, considered to influence the value of the cell for the next evolution step. So when we take a look, not just at the one rule, but the entire space, for instance, when we use r equal to 1, for r equal to 1, we're actually considering one cell to the left and one cell to the right of the cell that we're going to be evaluating. So there are 256 rules, and they have been explored throughout the years. They've been used for many explorations of areas, etc. If we make R a little bit bigger, 3.5, which is actually, and using cellular automata and Mathematica, will be 2 cells to the left and 1 cell to the right. Now the size of the space is 65,436 rules. And this space may not have been really explored as much as the ECA. But, this is really a small space compared to everything that we could have. For instance, if we go to a value of r equal to 2, now this rule space becomes 4 billion rules or plus, and this has not really been explored. And I know that there are a lot of things that we can explore in there, and it becomes really difficult to just, explore it. How do we explore it? How can we say, okay, we explored this area, now we're going to explore this other area? Because we really have never considered the spaces as if they were, that has some sort of structure. So how do we explore these big spaces? The general view of this, they have no particular structure, they're considered a blob. And there are many schemes that have been provided. There are, even starting back in 1986 with Langston's lambda, which he himself said that things were not working out with that, etc. There were many things that we tried to do in trying to make sure that we could, have some sense of structure. But at the end, we ended up simply just numbering them, from 0 to the maximum number possible minus 1. So, this particular ordering, has no, give us no hint of, any kind of structure, whether they are related or not. And we can actually do it in any, in many places, and we can go into the new kind of science, the NKS book by Wolfram, pages 55 and 56. You will see they show you pictures of that, where they are just numbers 0 to 256, and this particular manipulate shows, I'm not going to go into the 0 and 1/2, but for 1, you can actually see here, from 0, and it goes all the way to 256. So we can go for each one of these. So 0, 1, 2, 3, 4, 5, 6, 7, etc. And they will be in order. And this is the way that basically that most of the people will actually list and show the evolutions. And yes, there seems to be some structure like this one in here and this one in here. But in general, we'll find that it doesn't really give us a lot of structure, for all this. So we end up not having, for instance, this with the Sierpinski, we see them that they are, at a certain distance from each other, etc. But it doesn't really give you a lot of information on the structure. So we proposed some time ago a different way of modeling this. And this is actually a somewhat rebranding of that idea. So we use the concept of a rule gene. We first introduced an MB, and this is the references at the end of the presentation. But we used the word primitive at the time, but I think it didn't really have the right ring to actually be able to be understood. And so what we did with this, is we split each rule into genes, or a gene vector. And so each gene does not really evolve as a rule, but it defines the rule's behavior given that the value of the cell. So for instance, for k equal to 2, each rule is split into 2 genes, or a 2-dimensional gene vector, G sub 0, G sub 1. So the gene in position 0 defines how the cell evolves, given that the value of the cell is 0. And the gene in position 1 defines how the cell evolves, given that the value of the cell is 1. So we may say that each gene gets activated by the value of the cell. A value of 0 activates the gene in position 0, G sub 0. And a value of 1 activates the gene in position 1, G sub 1. Just as the rule number represents an equation of functions, so do the genes. So you may see the details in the reference under B. So these are some examples, quick examples of rules. These are rules that we have actually known, like 30. The genes are 6-3. For 135, the genes are 3-9. 23, we have the 90, which is 6-6. Very interesting. They actually have the same gene for both G1, G sub 0, G sub 1. For 110, you have 10 and 7. For 137, you have 1 and 10, etc. And this is for k equal to 2 and r equal to 1. But we can do the same thing for k equal to 3. And these are the series of these are interesting rules. These rules actually were provided to me a long time ago by Ed Pegg. He was looking for what he called pretty CAs and k equal to 3. So this is just a list of those, that he had given me. And these are the genes, these, as you can see, because k equal to 3, we actually have 3 genes for each one of them. And then we can look at them in this way. So we can now, doing something like this, we can now split the rules into genes. So what that serves us is now a way of structuring this. If I now order or this space into genes, and then, for instance, gene 0, the value of gene 0 is actually placed on this side, on the horizontal, and the G sub 1 is placed on the vertical. Now we can see that as you put this over here, this is a particular order for the genes. But if you put it in here, you will see that there is a symmetry. Right over here, you put it on the diagonal. And anything that you see on this side is actually the complement on the other side. So for instance, you have 110, and look at where 124, which is the reflection of that. If we go across here, you will find 193, and that's the complement. And here we have 137, which is the complement of 110. The same way that you will find rule 30 over here. And then if you go across here, where are you? right here 135, which is the complement for this one. So there is a symmetry with respect to this. As you can see, this one over here, you will find it right over here. This rule over here, 70, you will find the complement of right over here. So we're able to see, you know, this symmetry. You know, you see here the 99 and 157, or the 93 and the 69. You know, they are all, you know, the complement. You find also there's a symmetry in terms of the reflections. There is symmetry with respect to negated rules, inverse rules, also, you know, the reflection, I said, the complement. And if we can actually do this as well, of course, in 3 dimensions, 4 dimensions, you know, for k equal to 3, equal to 2, etc. So we can expand this and go from this. Of course, in 3 dimensions, it's kind of difficult to actually show this, but we can take slices on this 3-dimensional space. And I've done that, where you can see the structure of the cell. So you take a slice, you know, 2-dimensional slice of the space. We can do that also in 4 dimensions, you know, because those are, you know, very difficult to visualize. So anyway, we can see that doing something like this will allow us to explore the space, and actually this kind of behavior continues into bigger spaces. I don't have it here running for 3.5 because it takes a long time to render, but you could do that. In fact, I have an entry in a Wolfram forum where there's a notebook that actually have it enabled for 3.5. And in fact, you can do that in here. You can just put one more value for the R for 3.5, and then you can just run it. So anyway, so this idea of genes, you know, also allowed us to look at this in a different way. So even though the layout of the rule spaces will give us a glimpse on how the rules and the behavior are distributed in the space, we may also, you know, observe, you know, as you can see, if we go back in here, for instance, look at this. You have the Sierpinski right here, you know, so this gene has certain particular aspects for that. You know, the same thing with this one. Look at this, they all grow this way. So this gene over here has definitely a variance in how that behaves. All right, so we can do this, but we can also find, in it, without going into much detail, is that every gene that of a particular rule, for instance, for the ECA, it happens that the genes are rules for the space for R equal to 1/2. And every gene or the rules or R equal to 1/2, they're actually rules in the space for R equal to 0. So we have some sort of a hierarchy in that case. So we can create a sort of an ancestry for a given rule. For instance, I have a rule, then I split it into the genes, and they said I can then have those genes, which are also functions, you know, actually play out in the smaller space and see how they behave, and those in turn, until I actually have a tree, which, by the way, I'm looking forward to version 13 of Mathematica to be able to display the trees directly. Instead of using the graphs that I'm using right now. Anyway, so we define, you know, this genealogy tree as a graph where a rule is related to its genes, and its gene is, you know, it's a rule function in a smaller space that is also related to its own gene, so on and so forth, until you actually get to the most primitive functions that actually exist in this system. All right, so this is a manipulate with genealogy trees, and this is, unfortunately, right now, I have not resolved this issue on how to show this in a little bit smaller, but this is 110, and these are the 2 genes, you know, for making 110, and these are the very bottom genes over here. This is to the right here, the number is the R, and this is 10, and R equal to 1/2. 7 R equal to 1/2, and these are 0, 3, and 1 for R equal to 0. So this is the genealogy for this. I can actually say 30, and this is for 30. So the 2 genes are this one in here, and this one over here. So, where we have these two, and then we have the most basic ones, which are 2 and 1. So we could have, for instance, 90, which it happens to have the same. So 90, which is a Sierpinski, like this, which is also self-reflective, is actually composed of the same gene for both gene 0 and gene 1. So we have it in here. And then, of course, this one is composed of 1, which is the, what would be the complement, the reverse, it reverses the output. And then 2, which is the identity. So we can do this, each one of this, and we can explore each one of the trees, etc. And let me see, now go to the next. So we can use this, for instance, to compare rules. So let's take a look at the genealogy trees for 30. So in 30, we use 6, and I believe this is gene 0, and this is gene 1. So this is the 6 and 3 for a half, R equal to half. And this is 2 and 1. This is identity, and this is the complement function. So this is how, this is the way that we make 30. Now, 135 is the complement of 30, which is this one over here. You can see that it is, we're actually feeding these exactly the same input, etc. And now we look at the genes for 135. We find that the gene 3, which is actually shared in between the two, except that gene 3 in this case, I believe, is going to be on gene 0 position. And we have on gene 1, we have 9, which is in fact the complement of 6. And this is really the change in between the two, because we're, in terms of the number of genes or the genes that we're using. So this one here, 3 and 3, is common for both of them. And by swapping the position and also using a different one in here is sufficient to actually create a complement. So when we go all the way to the bottom, we still have the identity and the complement, or complement here and an identity. So we can see that the real difference between these two is, is this gene. And of course, swapping the position. If I don't have it here, so that we could look at how that's performed. So let's take a look at the next slide. So, for the idea of having genes, in the information of rules, yields the possibility of splicing rules from one rule space into another for a different value of K. So I decided to say, okay, now that I have that, I'm going to have, for instance, I'm going to take a rule in K equal to 2 or equal to 1. In this case, I'm taking 110, it's famous. So just name dropping at this time. So then I splice it and make a rule in K equal to 3, R equal to 1 that has the same behavior. So here's 110 to 1, and this is evolving for a single cell. And this is the rule, which is a big number. And K equal to 3, R equal to 1, and there's the behavior. It's identical behavior. You'll not be able to, in this case, to distinguish between one or the other. I did the same for 30. So this is the rule 30, and this is the rule, which is actually rule 30 spliced into this bigger space, K equal to 3. In other words, this on the right, we can say that they're genetically engineered, because I actually created them. I didn't go and look for it. I just took the gene from this one and spliced it into an identity. I took an identity rule, and then I spliced this, and now this became, the same as this one. So that rule splicing is also provided at the end of this presentation. So you are able to actually experiment with that. Okay, so, and I actually done that with k equal to 4. Actually, I've done that with k equal to 10. I've moved of all those realms. So the code will work for all that. All right, so let's take a look at the next slides. So what happens with the genealogy trees for splice rules, right? You know, if we look at this splice rules, for instance, 110, right? We have a 110 where we have 10 and 7. You know, this is the, I believe this is the identity. Is it the identity? I think the identity in here. So, and this one over here, you know, will be complementing. That gives us 110. All right, so we know what the genes are under this particular space, and these are the very bottom genes, you know, for forming these other rules. So what happens with the spliced one in k equal to 3 that we had before? So this is 110 again, and you know, we'll have to look at it, you know, side by side. But this one over here is the same as this one over here. And this one's here, the 7, is the same as this one here. So even in k equal to 3, we have that these are the same genes that actually make up the rule. This gene over here, which is the third gene, is effectively inactive. You know, it's a gene that is not doing anything. You know, this is, I would say, it gives you the identity. It doesn't do anything. It doesn't provide anything, etc. And if we go down to this one in here, you know, this will also be, you know, the same. As you can see, you know, they are the same genes all the way to the bottom. What you have in here, very, very similar to that. All right, so this is, you know, that's the genealogy of the, did I have, let me see, did I have, yeah, I had this here side by side. So this is 110, and this is the spliced. You see, you can see here, these two and these two. This one here is not showing. I think I will have to scroll it to the right. But you know, they are basically the same functions when you splice them or not. Okay, so I'm going to do the next slides. So in conclusion, I wasn't sure whether I'm going to have enough time to share some more of this. You know, the approach presented here is useful in providing insight in how to make up, you know, into the makeup of cellular automata rules and how they relate to their components, the genes. You know, it partitions the rules, rule space in such a way that gives sort of direction in, you know, and how to search. Not only how to search, but also how to genetically engineer some of those rules. You know, it provides the idea of genealogy trees, you know, to study the different parts of the rules that might be responsible for particular behavior. So we may isolate particular genes that may be of interest, and even splicing, as you saw before. I've actually done some explorations, and I didn't have that in here. Wasn't sure whether I will have enough time, but I was looking at reversible rules in the spaces, and I found out that it was interesting that the reversible rules, when you look at the genes, there are reversible rules in the smaller spaces as well. So there seems to be some sort of a structure in terms of the reversibility or the reversible rules. I know that Wolfram listed 6, the 6 reversible rules in ECA, which actually, in fact, are 2 rules are coming from R equal to 0. 2 other rules are coming from R equal to 1/2. And the last 2 rules are actually in R equal to 1. You know, all those, when you look at how the genes are, etc., you will find that the reversible rules actually have reversible genes as well. You know, I haven't looked into all that, but in more depth. But that's not only true in k equal to 2, that's also a true in k equal to 3. I'm actually I'm exploring in the space and where they are distributed in k equal to 3, these reversible rules. According to Wolfram, there are 1,800. I don't have the list of those, but I've been just searching myself, and there is some structure in where they are located, and also their genes are also reversible, have reversible characteristics. So anyway, here are a couple of the reference that I have for was talking. The code is provided at the end of the presentation, and I would now entertain any questions that you may have. And
someone just popped in and asked her questions.
Oh, okay.
Robert Nakabar asks, are the genes described in the paper?
Excuse me?
Are the genes described in the paper?
Yes, they are described real quickly in here in the presentation. I do not have a paper in the specifically for this, but in this reference, the partitioning of cellular automata rule spaces, even though I use a different name for the genes, I use the name primitives, they are fully described in that paper, and that paper is available in complex systems. I'm also working on a paper for Physica D, where I'm actually providing a unified model for all one-dimensional cellular automata, and where I actually fully describe this view of the genes. Yeah, in fact, if you look at the code here's the manipulation. This is rule genes. If you provide a rule for the K and an R, it would actually give you back the genes. And if you take a series of genes, like a list of genes, given a K and an R, you can actually construct the rule. These are, for splicing. And these are gene sets not suitable for K greater than 2. And this is the genealogy trees. These actually create graphs. One for just the rules and one for the evolution of the rules. So at least with this, you can see how they are, how every rule can be split into rules. And this code work for any K, any R. So you'll be able to take, K equals 15, R equal to, I don't know, 2, that's huge. And when you run it through this, given a rule from there, it will give you the genes for that. And if you take a series of list or a vector of genes, you can actually then construct it and give you what is the rule that it represents. Any other questions?
Robert asks, does your method handle gaps?
Say again?
Does your method handle gaps?
Gaps. What kind of
gaps in the R part of the divination?
Where?
He says gaps in the R part of the divination. I might be mispronouncing that. I can actually give Robert permission to talk in the Zoom. Let me see.
Yeah. Hey, Robert.
Okay, my question is about gaps. That would be in the parent row of colors. If, for example, with R equal to 1, you take the center cell and 1 to the left and 1 to the right. But you could also imagine skipping a cell. In other words, you consider perhaps the one above and 2 cells to the left and right, but in the sequence 1, 2, 3, 4, 5, you would ignore, for example, the second and the fourth cells. You'd only use 3 of them, even though they span a width of 5. I had a summer school student who was looking at rules like that.
Right. Now I understand what you mean by gaps. Yeah, it's in this case, no, this is, I'm actually going without any gaps. In part of the reason what I actually thought about something like that, you know, when we talk about, we think about a space, you know, and in this case, the space, it will be the rules, you know, I mean, the cells to the right or to the left. When you start skipping, you know, it's like you're transmitting information from far away in the space. So yeah, the behavior is going to be, you know, different, but the model, the way that I'm actually describing this, that if you can see in the code, it actually assumes continuity. So the only one that there will be, I guess, sort of discontinuous, that whenever you add a half, there will be 1 to the left. You know, so that's what it is.
Thank you.
Thank you, Robert. All right, so we'll then conclude it here. I appreciate everybody that came to the talk.